Don has his second part, ranking equivalent uranium, thorium, and potassium for uranium targeting.
So, hello again.
Hello.
We're going to have some fun with this one, I think, I hope. So, I got wrangled into giving the radiometrics talk 101 part because I wanted to give this talk. So that's part of the reason you had a geochemist give the first part. This is where I really get into what I am passionate about this idea of taking this data and doing something with it. And I just wanted to speak to one thing. This is the logo for my company, and it represents a number of things. So I'm Peridot Geoscience, but that's not a P. It's actually a rho symbol. And in statistics, we use the rho symbol to symbol correlation. So I'm really interested in the correlation and relationships between many, many things, including, in this case, uranium, thorium, and potassium. So I'll be really talking a lot about this idea of interrelationships and using those interrelationships to try and break out different groups that we need to pay attention to or not pay attention to, depending on our needs. So, Dave once mentioned to me that I should, the best thing to do in a talk is to tell people what you're going to tell them, and then tell them what you told them. So, that's the goal here. Summary of my objectives. First, I'm going to go through and talk about how I am establishing some uranium-thorium ranking to try and understand what uranium anomalies might be worth looking at. Next, then I'm looking at potassium to thorium and trying to create domains, like I showed in the GSC example, trying to model that behavior to try and isolate specific places, put my uranium-thorium anomalies in context. Compare those uranium anomalies within those contexts. Which ones are worth looking at, which ones aren't, based on my current assumptions about the model, for instance, or current assumptions about which ones might be a priority in the area. And then finally, our whole goal is to try and find anomalies and then start reducing them because they don't make sense. And then we're left with whatever's left, still a valid target, so it's still worth pursuing. So that's the idea here. Prioritize those domain-specific anomalies, reject man-made causes, for instance, and review remaining ones. So I'm going to walk you through what goes on in the brain of a geochemist looking, at least this geochemist, looking at this data. Most people, I'll say most people, this isn't always the case, but often we start with this raw data, both potassium and uranium, and there is sometimes a step to go towards a uranium-thorium relationship, maybe also potassium-thorium relationship. A lot of what I've been trying to do, and I was introduced to this before, this isn't completely unique to me, is this idea of taking a uranium squared over thorium approach to looking at uranium anomalies, but also looking at the potassium-thorium anomalies and ranking them relative to thorium. These start going into the world of discrimination diagrams, which we use in geochemistry all the time to try and block out, is this rock a granodiorite or a granite, based on mineralogy, for instance. The idea of breaking out different groups of data and using that to map. So, where this comes from was a pretty strong desire of mine to try and understand more and more about the regional geochemistry of the Athabasca Basin. And with the support of Eric Potter, through TGI-4, we decided to go in and mine the assessment records and all the available data that was public for the Athabasca Basin. And in doing so, one of the patterns that came out from this work was the idea that in the uranium to thorium plot, the uranium-thorium ratio doesn't actually represent enrichment of uranium relative to thorium. If you were to plot a straight-up uranium-thorium plot, it would kind of come up, cut right through here. And it wasn't as effective. So as we started to model this up and look at it in more detail, we realized that it was the uranium squared over thorium relationship that actually showed more value, looking at geochemical samples. So these are all rock samples. When we plotted up the ones that were near surface, so these would be either surface samples collected by ramokers, for instance, that had been run for geochemistry, or samples that were within the top 50 meters of a drill hole. We start plotting those up, we start to see correlations of these high uranium thorium anomalies with elevated thorium actually showing up over places like McArthur River. So these are essentially surface samples over McArthur River having this anomaly in them. And they're relatively spatially restricted. Now things like thorium, high thorium in these greens, again, are mapping out a lot of the MFB, MFC heavy mineral banding. We also had another couple of features that I spoke about in that talk, including yttrium, which is why yttrium is in blue here. There's some pretty interesting things going on geochemically. When it comes to radiometrics, however, we're left with only uranium, thorium, and potassium. So I backed off a little bit and just used these kinds of plots to look at that uranium-thorium relationship, but just specific to radiometrics, radiometric data. So that's what I'm going to be looking at. So just to emphasize, all of this data that I'm going to be presenting to you was downloaded from the GSC for free. These are all the compilation. This compilation in 2011 by Buckle et al. Is the geophysical series for the Athabasca Basin. And it was a compilation of all the surveys that had been done. So this is all free data. It is airborne, and so it's a little bit wider scale than you might get on your own property if you decided to fly it lower, etc. But I wanted to go through this and sort of show what the potential might be. So again, this is free data, this is accessible data to you. So the first thing I wanted to do was to look through and look at, based on this uranium multiplied by uranium divided by thorium, uranium squared over thorium, what kind of statistics and what kind of groups could I create from this to see anomalism? And so what I did was plotted up a scatter plot and looked at that, but knowing that this relationship is worthwhile from the geochemical work, I put it in and I selected these thresholds basically on some statistical breaks. And in order to sort of discuss the spatial relationships involved here, especially when we come to the potassium-thorium side, I brought in this. So this little box here represents this box, which is the area around McArthur River. This box here is right on the edge of the basin. And so we're including a certain amount of basement material, mostly Wollaston, and quite a bit of Manitou Falls B, especially. And one of the things here that I was doing was basically ranking these in pretty primary colors. So a yellow would be a pretty low-level anomaly, greater than 0.2, 0.4 being a slightly higher, and red being significantly higher than that. I cut everything off at thorium less than 1. There's a few reasons I did that. One, well, a couple reasons really. One, a lot of data at really low levels, there's concern about what happens in lakes when you have water attenuation, things like that. So in order to clip out all the lakes, essentially, I chose a level of 1 for thorium. So that's the reason why there's this white gap here. You'll see that consistently through. It's a little hard to tell here. Maybe with the copies that you guys receive, you'll be able to see the edges of the lakes a little bit better. But essentially, it's blocking out the lakes to make sure that the anomalies that would exist in a lake aren't being seen. Because the other flip side of using a ratio is that if you have a value less than 1 in your divisor, essentially, it's going to push your ratio up. So the idea was to cut it off at 1 so that you're not going to artificially raise your ratio. So, a couple things there as far as the plot. The differences between sandstone and basement, at this level, we're getting quite a few anomalies in the McArthur River area. The big whopper, of course, is McArthur River proper, because this was flown after the mine existed. So all these surface workings are lighting up like a huge candle. There are a few other anomalies around, which I'll talk about in a minute, but it's all about context, right? So this is all sandstones, essentially, with cover. When you get into the basement area, where you are going to maybe get a little bit more of basement-like rock being exposed, you can see there's a pretty strong uranium expression here. The question is this mineralization, or is it just the fact that these rocks might have had a higher tenor of uranium anyway, and they're being exposed by surface processes later? So there's always those other things that are going on. The idea here is to take these anomalies, especially these ones in the sandstone area, and find a way to start reducing them so we can decide what's important. So, most of my talk is going to focus in on McArthur River. But I'm going to go back to that regional story to kind of emphasize differences that I see, especially when we're trying to involve a basement story. So again, we have this uranium-thorium ranking. Next step, establish those potassium-thorium domains. And the way the GSC did it, so revisiting this, was to look at a ternary radioactive map and start manually mapping in things they see visually in that radioactive ternary. I'm not saying anything about that as being a process. I kind of like it in some ways. because they did mark out some interesting features. The relationship of all this to mineralization, I don't think I've pursued yet, but it's the same concept of what I'm going to do next, which is essentially taking those potassium, thorium, in this case they did potassium, thorium, uranium, and build up different domains that they considered worth considering. So what I did, and I apologize for the colors, when I did it on my own machine it looked a lot better than it does now, so hopefully you'll get the gist of what I'm trying to do. So the idea here, again, with the regional picture, and looking at the actual scatter plot of data, in this case, potassium relative to thorium, and especially looking down here in the corner where I have a slice of basement with a little bit of the Athabasca Basin, MFB, MFC, you can sort of see that there's these different subgroupings, which I've categorized here as a bit of a discrimination plot. And essentially what it breaks down to is that you've got a fair amount of basement-like material, of course, in the basement, but you've got a little bit kicking around McArthur River. As you move away into maybe a little bit more altered basement, perhaps, still relatively high potassium thorium, but it's the thorium content is lower. Not quite sure what that's defining yet. The idea is not always to explain everything, but to come up with some things to break things apart. And so we've got a bit of zoning of both this B and C, which would be a high potassium thorium with moderate thorium going into high thorium, and that's up here in this plot. And then you've got this group down here, which are essentially my group A's, which are high potassium thorium but low thorium, which I consider kind of an altered sandstone. So they're low in the 1 to 3 ppm, equivalent ppm of thorium, pretty low thorium contents. And of course you can see in the regional scale that's spread out a lot in here and around McArthur River. And then ranked by the relative potassium thorium, they go up. Now if you go below this line, 0.1, you get another group of samples. And this scatter plot is specific to this area, just to basically extracted the data for points for this area to emphasize this difference. And it's kind of clear that these have a distinct tenor than these. And so I use those breaks to apply to the McArthur River area. And the MFB and MFC that's mapped in here are clearly low in terms of potassium thorium enrichment, but do show distinct differences in thorium, and you can see that whole band of thorium content associated with the MFB and MFC. So I feel this has been generally successful at breaking out some domains. Pull out some ideas of things that could relate to real life geology. So again, we have our areas A, B, C, and D. And apologies for the fact that my basement doesn't match up with their D basement in the other one. So we'll just stick with this one for now. It'll be up on all the slides. So taking this, we then need to break out the different groups. There's a little box there that shouldn't be there. But basically the idea is, within each one of these different domains, what do the potential uranium anomalies mean? So if domain A is a high potassium thorium, low thorium, potentially altered sandstone, that's actually a pretty good target for a uranium anomaly. Especially if those uranium anomalies are actually making it to surface within a sandstone, which is our target rock, at least in this area. Domain B, it could be basically a slightly an altered high thorium sandstone, such as an MFB that has been altered, or it could be a low thorium basement. And again, some of these basement materials could be there because of a number of reasons. One of the more popular ones is glacial. Again, I have some differing opinions about that, but we'll go from there. And domain C is a much more extreme version of high thorium, high potassium thorium anomalies, and they are definitely, as we saw from the previous map, a lot more basement-like. And then finally, we have our little groups of low potassium thorium enrichment, high thorium samples, which are getting into the high thorium sandstones like the MFB, little bits and pieces popping up. So the next step would be then to compare those uranium thorium rankings versus the potassium thorium domains. So essentially what I'm doing is I'm taking all these guys and dropping them right on top of these. I'm saying, well, what does this mean? So we start with that, and then we add in these anomalies. And what I've done in the next slide is actually circle up. So all of these yellows, and unfortunately on this map it's a little bit hard to tell the yellows from the background, but yeah, especially now with new colors. But what I did was I circled them in a contrasting color to try and help follow that. So what I have in the, for instance, in the sandstones, the highly altered, potentially highly altered sandstones, I ring them in blue. And in green for this group, etc. So we're going to follow through from that. In this environment, if we have a strong basement signature, something that's clearly got a high thorium signature, correlating generally with what we would consider basement rocks, like granitic boulders being thrown onto this property, those might not be our best targets. So one thing we can do is go through and start reducing these anomalies. So the idea here is to say, well, you know what, if it's not the kind of waterfowl I'm after, I'm going to just start ignoring them. So essentially what we got here, domain C, I'm saying, no, we're not going to even bother thinking about those anymore. So I'm already starting to reduce my anomalies. So what I'm going to do next is essentially I've blocked out these high potassium thorium, high thorium anomalies that would have existed in here. I've taken this group of sort of potassium thorium group and overlaid it on top. Just said, let's blank it out. We're not going to be concerned about those. So we're still left with quite a few anomalies flying through here. So like any group, we're trying to reduce these anomalies. And this is a little bit better image to try and show the distribution of a lot of these anomalies. So again, we've got quite a population in this green of high potassium thorium, moderate thorium anomalies. We've got a decent population as well of, again, getting into altered sandstone, which are ringed in blue. And then with these purples are these low potassium thorium, high thorium anomalies, which would be little blips and bops kind of in different spots around here. So the next step would be, if we clearly know that, say, the McArthur River mine site is causing us a problem, what else is causing us a problem? Like, what are the things we can actively ignore because they're not going to be natural? And the road is here, and there's some spots along the road that are lighting up. The question is, would the road just light up? If there was a spill, maybe, but I don't know of any that have occurred. But what does pipe up, there's a core storage right here. And that lights up like a, again, like a candle. It actually is, if I back up just a slight bit, that's this right here. And if I try and get, I don't know how far back I can go. But essentially right here, you've got a pretty good spot of exposed uranium-bearing material at surface. That was there when the flight was flown. So, yeah, not a target. Gravel pit. Right here, there's a gravel pit. That too is lighting up on this map. Well, it's not hard to tell. I don't want to go back too far. But essentially, right in here, there's an anomaly where the gravel pit exists. So we can clearly knock those out. Those are not part of the system. What we're left with, well, fortunately or unfortunately, we still also have quite a large group of anomalies. But this is actually starting to take some shape, though, which is kind of nice. So then, the next step would be to think about, well, what else might be involved here? Is this just exposure? Are some of these anomalies, say for instance, these ones that are, say, univariant, they're an anomaly, uranium anomaly that's in one type of domain. So one rock type essentially, and it's showing a bit of uranium enrichment. Well, that could be affected by the idea of a structure coming through and things just getting mixed around a little bit. And as you look at some of these, you'll start to see some of them actually line up with each other. You'd almost see that sort of northwesterly trend to some of the potential structures that are actually crossing this area, and there are quite a few. So maybe it's more important to look at where there's clusters of anomalies. So changes in uranium thorium host with a uranium anomaly in them. So for instance, right here, we've got a whole collection of, there's this broader area that's associated with one domain, but then right on the edge of it, you've got a number that are associated with another domain. You know, a lot of stacking of things that are a little different from each other, but still showing uranium enrichment. Maybe it's not due to just the rocks they're coming from, but actually an overlap of features. And then also distinct uranium thorium enrichment. So right here as well, where we get this group of stacked anomalies, we're also getting a distinct jump in the actual uranium enrichment signal. And then finally an overlap of those features. So when you've got distinct enrichment of uranium, plus spatially associated changes in host to those uranium enrichments, maybe that's telling us something. So when we start circling these things, say changes in uranium and thorium host, possible mobilization, you get these green circles that I've drawn on here. Where there's distinct uranium thorium enrichment, you get a red. So I've got a bit of distinct up there, got some distinct down here, down here. Where you've got both, I've put in this pink. And this is an example right here. So the idea is to start to think about what is causing these. And could they be of value? But I've already started to reduce the number of anomalies that I'm thinking about. Which is our goal, right? At least it's my goal. And when I start looking at these things, I start to recognize that there's trends. So for instance, here to here to here, that's almost on trend with a kind of a P2-like trend. And remembering that this area, and this is probably the reason why I kept this map as an underlay, there's drumlins all through here, and Garnet referenced the drumlins that are all through here as well. So just because the signal isn't necessarily continuous doesn't mean they're not linked. Because there may be gaps, that overburden problem, soils blocking out signal. There may still be this problem. There's still lots of other stuff going on. But it is kind of interesting that they do tend to line. You can start to draw some lines, and it's always fun to draw lines and then erase them and draw them again and think about something else. But what I wanted to focus in on was this group right here. Because you can see this fairly strong grouping of both a strong uranium, relative uranium enrichment of that uranium signal, along with the clustering of other sort of multi-host uranium anomalies. And when you actually go into what's there, it's actually a boulder terrain. So the Reed Lake boulder terrain starts right here. So when I went into the records and pulled out the radioactive boulder systems that are on record in the Saskatchewan survey, the Atlas, and I pulled up the ones that were over 10,000 CPS, and then 5,000, 2,000, so reds and greens are of course the higher grade values. You can see a bunch in here, there's a few down here, there's a little yellow guy down there. There are some boulders that have been recorded in that system, and if we focus in on that zone, you get this clustering of boulders right here, and then it tends to extend down through this, even extend it from here down through this group. But this may be potentially the source for this boulder terrain. And from recent history, we know that boulders can be useful for still finding these deposits. We spent a lot of time in the past looking for these boulders, and some of that did end up pulling people into generally the right area for a target that was eventually found. Maybe we can restack and relook at radiometric data and think of it geochemically and come up with some other targets as well.
5 minutes.
So right now I'm at my summary, so we're looking pretty good here.
Magic.
So again, just to review tell you what I told you. The summary of objectives really was, one, I needed to establish that uranium thorium ranking. And again, this is based on modeling that I did based on actual geochem samples and some patterns of distribution that are challenging my conceptions about what the models actually are. But the idea is to really model that, treat it empirically, rank by intensity, and see what falls out. Next thing, create those uranium, potassium, thorium domains using a geochemical discrimination plot idea of potassium thorium ratio versus the actual thorium content, and create these little zones. Then third, compare those uranium anomalies versus those potassium thorium domains and decide which ones I think are actually valid for the area. And this may change place to place. Even the actual ratio value and the thorium values might change. But the idea here is not necessarily to say this is the be-all end-all. It's the idea of thinking about the data and working with it. And then step 4, review the anomaly distribution and prioritize some of those anomalies based on their spatial distribution, but you can then also take it to the next level and start bringing in other geophysical models, such as being able to relate some of these to actual structures in the basement, mag features, gravity features, resistivity features, stacking all of these and deciding what are the really important pieces that are important to finding a target in this area. And I think, aside from the fact that, well, I guess it's the primary fact that these data sets contain uranium. This is actual compositional information specific to the element we're interested in. Again, it's at surface, and you may have your arguments against that. I like it. But the fact that it's actually measuring uranium and we can model that behavior means that it's still significant. So with that, I'll end.
Any question for Don?
How does a gravel pit become an anomaly?
Well, if that was in line with the other anomalies that were there, for instance, if those anomalies that were on strike of it, just to the north of it, say, okay, this is okay. So right here, that's essentially that gravel pit, right? So if these two anomalies here are part of the same group of anomalies, and you happen to put your gravel pit in the spot where one of these anomalies already existed, but you just exposed it even more, you may actually create a stronger signal.
It shows up.
Which, the gravel pit?
Yes.
Yeah, the gravel pit actually has a strong uranium signal in it.
Why?
Because it's actually got gravel. It actually had uranium. My understanding is that is the gravel pit where they actually pulled out a few pieces of uranium.
I mean, it's not a natural gravel pit. It's
No, this is one they dug out. This is one they were using for work around the
Okay.
area.
Question?
Yeah, if that's it. No.
So that's the
Set?
end of
It's a good way to make a radioactive road.
It can be. Yeah.